This is lecture 27. We're going to talk about enzymes today. We'll start with metabolism, just a brief overview of what it is. Then we'll get into how enzymes work, how they function, and then how they're regulated, how we can control the enzymes. So, metabolism, this is the sum of all of your chemical reactions. Some of them are anabolic, some of them are catabolic. Put them all together, and you have your metabolic state. Meta just means after. So, after all of your anabolism and your catabolism, your upthrowing and your downthrowing, according to their literal definitions, you have your afterthrowing, according to its definition. So, again, the sum of all chemical reactions, that's metabolism. And enzymes, they're like real estate agents or stockbrokers of the metabolic marketplace. Not every transaction is going to involve a real estate agent, right? And not every chemical reaction is catalyzed by an enzyme, but for the most part, that's how it works. And enzymes can make those reactions, those chemical reactions occur billions of times faster than they ordinarily would. Like they would occur without the enzyme, like eventually without the enzyme, they would, take place. But with the enzyme, it might be, 1,000 reactions in a second per enzyme. So these are really fast. Some are faster, some are slower. But even the slow ones are still sort of fast, right, relative to the hundreds of years it might have taken otherwise. So if your enzyme concentrations were to fall just a little bit too much, which isn't that much of a change, you wouldn't be able to survive because metabolism is the foundation of life and it's conducted by enzymes. So preservation of life requires an abundance of them. So how enzymes work is they take substrates or reactants and they elicit products. So a substrate or a reactant goes in, the chemical reaction happens, and then a product comes out or products. It depends on the reaction. So what enzymes are doing is they lower the activation energy of the reaction, and that just means activation energy. This is the minimum amount of energy that's required to undergo change or carry out whatever function is happening in the reaction. And so enzymes reduce it. They reduce the activation energy. Heat might be able to facilitate the reaction as well to lower the activation energy, but the temperature necessary to do that would like kill the cell. So enzymes are how our metabolism works at a speed to support survival. So this is called catalysis, lowering the activation energy with a catalyst. Think of it like a Black Friday, like Black Friday prices, or those managers special stickers that they put on old expiring meat that's gray. If you reduce the price of stuff that nobody really wanted in the first place, people race for those shelves. I mean, the meat probably sat there at full price for a week and a half, never would have sold. The TVs and kitchen appliances and whatever have sat on those shelves for 11 months at full price. They would have never sold. But the discount sticker goes on, and people are trampling other shoppers to death to buy it. So that's basically what enzymes do. They make chemical reactions cheap enough to like fly off the shelves. So the function of enzymes is based on their shape, the affinity, which just means the strength of their attraction, is literally based on their curves. So if the affinity is strong, the pairing is going to happen. The substrate and enzyme form relations, and then the chemical reaction happens. So each substrate has a specific enzyme, and vice versa. Each enzyme has a specific substrate. Substrates can't just plug into like any old enzyme. There are specific pairings. It's like a match made in heaven. It's like Disney relationships, right? Where there's one soul for me, or it's like on the slide here, plugs and sockets. The substrates would be the plugs, And then the enzymes would be the sockets. If you've been to other parts of the world, everywhere has its own plug and socket system. So the electronics you bring from home don't plug into the wall. Like in the US, we have type A and type B, those two prong and three prong, like the grounded three prong sockets. Then it's like type C, those are the European two prong ones. The amps and volts are all different. And so you just go to other areas throughout the world and you see these different prongs and different amps and volts and everything. But the point is there's a specific socket for every specific plug. You can't just plug whatever into whatever. And enzymes work similarly, except there are thousands of them rather than like 15. There are thousands of plugs and sockets, each with a single match. So when substrates bind, creating that enzyme and substrate complex, there are lots of different reactions that can occur based on which substrate and enzyme are interacting. And each of these has its own unique effect on your metabolism. And there are tons of ways to control the enzymes themselves, ways to facilitate or inhibit the activity of those enzymes. And if you do that, if you manipulate the behavior of an enzyme, there will be downstream consequences. There will be metabolic implications. And this is really how the pharmaceutical industry works. Most pills that people take are enzyme modulators of some kind. So we'll talk about 8 different ways to regulate enzyme function. These are the 8 ways, and I'll explain how they work, how each one of these works, and then I'll give you an example of a drug for each mode, or some sort of reaction for each mode. So beginning with allosteric control, which can be positive or negative regulation. Usually we're talking about negative though. But allosteric activation, that's positive modulation, meaning more enzymatic activity. And then allosteric deactivation would be negative modulation, meaning inhibition of the enzyme's activity. So the allosteric site on an enzyme, it's an alternative binding site. Think of it like an electronic device with multiple sockets. You can plug multiple things into it. One of those sockets would be the active site. That's where the substrate binds. That's where the chemical reaction happens. But there's also an alternative site, and that's where other stuff can bind. And when other stuff binds there, it can change the shape of the active site. And remember, the shape of the active site, literally the curves, determine affinity between the substrate and the enzyme. So allosteric activation would happen when something binds to an allosteric site, and that changes the shape of the active site in a way that makes it more enticing. It strengthens the affinity between the enzyme and substrate. And then allosteric deactivation, that would be when something binds to an allosteric site and it changes the shape of the active site to make it less enticing. It weakens the affinity between enzyme and substrate. So an example of allosteric deactivation is PFK and ATP. PFK is phosphofructokinase. It's an enzyme in glycolysis. Uh, People usually, very commonly, refer to this as the regulatory step in glycolysis, although any step could really be regulatory. But the regulation here is through allosteric deactivation, through inhibition. So you consume ATP at this step in glycolysis. The commonly reported math of glycolysis is that it produces 4 gross ATP per molecule of sugar that runs through, but it consumes 2 to get started. So glycolysis nets a total of 2 ATP. That's both true and false. It's true when hexokinase is the first enzyme in glycolysis, which would make PFK the third step. But you don't need to use hexokinase. And during exercise, you suppress it a bit. And so we'll talk about that later in this lecture. We'll talk about the suppression of hexokinase. But for now, let's just talk about PFK, and let's call the third enzyme of glycolysis. And it is one of the ATP consuming ones. PFK does consume ATP. Hexokinase would be the other ATP consuming enzyme if you actually used it to phosphorylate your glucose. But PFK is the ATP consuming enzyme in glycolysis that you can't skip. And at the bottom of the image here, of the enzyme picture, you see the active site. You see the substrate there, fructose 6 phosphate. That's the substrate for this enzyme. But you also see ATP bound there because this reaction consumes ATP. But the purpose of glycolysis is the generation of ATP. So if you already have a ton of it, if you have a ton of ATP already, there's no point to continue running glycolysis at an elevated rate. So the excess ATP will bind to an allosteric site, and you can see that at the top. The allosteric site is at the top of the image. And that changes the shape. If ATP binds there, it changes the shape of the active site. Like it gives it a horrible haircut and makeover, the enzyme. And so the substrate is no longer attracted, it's no longer interested. So that's an example of allosteric control. Competitive inhibition, this second form of enzyme regulation. This is when the inhibitor binds to the active site and it just sits in that seat. It occupies that chair. So the substrate can't get access. The substrate can't sit there. And so think of it as like a monogamous relationship. The enzyme won't date two substrates at the same time. So if the inhibitor gets there first, the substrate's out of luck. Um, and so an example, a pharmacological example would be antiretroviral drugs. And so Emtreva, this competitively blocks reverse transcriptase. So its main effect is competitive inhibition. And then zidovudine, this competitively blocks DNA polymerase gamma, which is what maintains mitochondrial DNA. So some major side effects of zidovudine are going to come from competitive inhibition, not its main effects, but its side effects are from competitive inhibition. And I'll talk about that one again later. Moving on to non-competitive inhibition, the inhibitor and the substrate. Sorry. Sorry if that was super loud. The inhibitor and the substrate can be bound to the enzyme at the same time, simultaneously. So the inhibitor does bind to an allosteric site, but what makes this different from allosteric inhibition is that the substrate affinity doesn't change. What changes is the activity of the enzyme, the chemical reaction itself. The substrates just don't elicit products. And then also, the inhibitor has no preference regarding whether the enzyme is bound or unbound. So that's a distinguishing feature of non-competitive inhibition. So, like, is the enzyme already bound to its substrate? I'll happily bind. Is the enzyme currently free? I'll happily bind, right? The inhibitor doesn't care. It just sits in that seat and ruins the reaction. It heckles the active couple. So there's no active coupling. So that's non-competitive inhibition. And an example of it would be lead. So when people talk about heavy metal toxicity, they're often talking about lead. I mean, there's also mercury and cadmium and arsenic, but lead is a common one, which nobody makes pencils and paint and gasoline out of anymore, but they used to. That's why it's so common today. But it exerts non-competitive inhibition on the enzyme that zinc binds to and is supposed to sort of like mate with, but it's heckled out of that role by lead. It's heavy metal toxicity. So the next one is uncompetitive inhibition. And this one is different from non-competitive inhibition. So sometimes it's called anti-competitive, but uncompetitive inhibition is, quote, Potentiated by the substrate. That's the expression you always see. It's potentiated by substrate binding, which means the inhibitor won't bind. It can't bind until after the enzyme and substrate have bound. Then the opportunity to bind becomes available. Uh, so if you look at the socket in the bottom right, once that plug, which represents the substrate, is inserted into the socket, which represents the active site, this happens, right? The site for the inhibitor becomes available, and then the inhibitor can bind. So if the enzyme isn't bound, the inhibitor can't bind. Then once the substrate binds, the site for inhibition is available, the inhibitor binds, and then it exerts its inhibition, exerts its effect. So, lithium is an example for bipolar disorder. Lithium is an uncompetitive inhibitor of inositol monophosphatase, and uh, this is involved in the generation of phospholipids in the phospholipid bilayer. Bipolar disorder has an excess of substrate, so a lot of phospholipid turnover. And in the presence of elevated substrate concentrations, uncompetitive inhibitors are much more effective. So that's what makes lithium effective here. Okay, we're halfway through our list. Mixed inhibition, that's up next. And this is pretty much the same thing as non-competitive, except the inhibitor does have a preference of whether the enzyme is free or complexed. In non-competitive, the inhibitor doesn't have a preference. It doesn't care. In mixed, it does. And it can affect affinity for the substrate, but it does decrease the reaction rate. And you'll see mixed in the literature on occasion, but it's not one I'm going to hold you accountable for knowing here. But just a glimpse at some literature chatting about it. Both of these studies are talking about ACE inhibitors, um, blood pressure medication. And in the top one, they're also talking about um, encapsulinase. And so, like atrial natriuretic peptide, which we've mentioned before, with its role in lipolysis, this is a peptide, ANP, atrial natriuretic peptide. This is a peptide that's secreted by the heart, by the atria, and it lowers blood pressure. If it's inhibited, blood pressure goes up, and uh, encapsulinase is the enzyme that inactivates it. So if you inhibit enkephalinase, the blood pressure will go down or it'll stay down. So the next one up, this is suicide inhibition. And this is like competitive inhibition, but it's not reversible. Competitive inhibition is reversible. It's not a marriage, it's just a date. But with suicide inhibition, there isn't a quick breakup that can happen. It's irreversible. And the inhibitors that bind to that active site, just like competitive inhibition, the inhibitors bind to the active site, but they're derived in this case from the enzyme's real substrates. So the enzyme initiates the reaction, and so it starts catalyzing this reaction, and then it reaches a point where it can't go any further because it's not actually the substrate, but it's stuck in that relationship. So examples of suicide inhibition, aspirin is one of them. That's how aspirin blocks cyclooxygenase, the COX blocker, right? Cyclooxygenase inhibitor. That's a suicide inhibitor of it. So it's irreversible, whereas ibuprofen would be reversible. And then also zidovudine. I said I would cover this one again later. This is the antiretroviral I mentioned in its the competitive inhibition section. I talked about it. So it's a competitive inhibitor of DNA polymerase gamma. So mitochondrial replication is a side effect, but its main effect, the main effect of zidovudine, what it's actually prescribed for, that primary action is a suicide inhibitor of reverse transcriptase. So next up is accumulation of product. And Earlier, when we were talking about PFK, phosphofructokinase, I mentioned hexokinase, the first enzyme in glycolysis. And I also mentioned that it doesn't have to be the first enzyme in glycolysis. So, as the name suggests, hexokinase, it's kinasing sugar, right? It's attaching a phosphate to a hexose, six carbon sugar, to the sixth position, right? Making it a G6P glucose 6 phosphate. Hexokinase, hex, right? Six, or like an evil spell. But so hexokinase attaches a phosphate to glucose, making it glucose 6 phosphate to the sixth position. But there are other ways to get G6P, glucose 6 phosphate. You don't need to use hexokinase. And so we'll talk about it in just a second when I'm describing the next mode of enzyme inhibition. But when you accumulate G6P, it backwardly inhibits hexokinase. In this case, allosteric inhibition, but accumulation of product can inhibit in tons of ways. So the product generated by an enzymatic reaction can exert inhibition of that reaction once you have enough of it, once you have enough of that product. It's a very immediate form of negative feedback. And hexokinase is one example of that. So, how else do we get G6P other than through hexokinase? Um, let's look at phosphorylation as a mode of enzyme regulation. And we'll spend the most time here because it's going to lead us into the lectures that come next. So, phosphorylation can toggle the active and inactive forms of an enzyme. It's like flipping a light switch. You can flip it on or off, and phosphorylation can do both. Depending on the enzyme and depending on where the phosphate is attached, it could turn that enzyme on or off. So the two enzymes we'll talk about are glycogen synthase and glycogen phosphorylase. And when these get phosphorylated, it changes their behavior. Again, phosphorylation is the attachment of a phosphate, which is just a phosphorus with four oxygens connected to it. Thousands of different proteins reside in your cells, and a ton of them can have their behavior changed by the addition or removal of a phosphate. And phosphorylation can occur on multiple sites of those proteins. So phosphorylate one site and it might turn it on, phosphorylate a different site and it might turn it off. And then abnormal phosphorylation, this is a major cause of human disease, but kinases are the enzymes that do the phosphorylating. The kinases are enzymes that attach phosphates, and the enzymes that remove the phosphates are called phosphatases. So kinases attach phosphates, phosphatases remove phosphates. Okay, let's look at glycogen phosphorylase. This is the enzyme that initiates glycogenolysis, not glycolysis, but glycogenolysis. This is the chopping up of a chunk of, chopping off of a chunk of sugar from your glycogen. So you have a big hunk of complex carbohydrate, your glycogen, the storage form of carbohydrate. But you can't consume glycogen whole, right? You have to break it up into individual chunks of sugar first. And glycogen phosphorylase is the enzyme that cleaves off a little chunk of sugar to be burned. That's glycogenolysis, glycogenolysis. You're lysing glycogen, glycogenolysis. Now, if we're in skeletal muscle, the enzyme is going to be called myophosphorylase. I mentioned this earlier in an earlier lecture in reference to growth hormone. So, patients with McArdle disease have a deficiency of myophosphorylase. And so these patients don't experience a rise in lactate during exercise. And so they don't get a subsequent rise in growth hormone from the exercise because lactate is a major trigger for growth hormone release. But that's not what we're talking about here. We're just talking about the enzyme itself, and that enzyme chops a G1P off of your glycogen. So G1P is glucose 1 phosphate, which means it's glucose, right? But it's already phosphorylated. Plain old glucose doesn't have a phosphate attached. G1P, glucose 1 phosphate, has a phosphate attached at the first position. G1P, at the first position, there's a phosphate attached. But from there, you just have to move that phosphate to the sixth position. And that's what phosphoglucomutase does. Phosphoglucomutase moves the phosphate from the first position to the sixth position, first carbon to the sixth carbon. So now you have G6P, you have glucose 6 phosphate. Um, so glycogen phosphorylase or myophosphorylase chops an already phosphorylated chunk of glucose off of your glycogen and of your stored carbohydrate. Uh, but the phosphate is on the wrong carbon, so phosphoglucomutase moves the phosphate to the correct carbon, the sixth one. Now you have G6P. And remember, G6P, that's the product of hexokinase. So what people say is the first enzyme in glycolysis, hexokinase, creates G6P out of glucose. And the hexokinase is definitely the first glycolytic enzyme in yeast, right? And sometimes it's the first glycolytic enzyme in us, but not so much when you're exercising. When you're exercising, glycogen phosphorylase is the first enzyme in glycolysis. And then phosphoglucomutase would be the second. And then now you have G6P. That's the thing that backwardly inhibits hexokinase, and you never bothered to use hexokinase to create it. Now, we'll talk about why this is important to human performance and survival later in the semester. At the end of the semester, we'll talk about these different pathways through glycolysis, why they're critical. But for now, let's just talk about the enzymes. It begins with PKA signaling, protein kinase A, PKA. We've talked about this enzyme before. It's a kinase, it's a catabolic kinase. The stuff it phosphorylates has catabolic actions. So here with carbohydrate catabolism, PKA phosphorylates phosphorylase kinase, and that activates so that activate like it gets activated. But then that activates glycogen phosphorylase, which activates that one. So glycogen phosphorylase then chops a G1P off of your glycogen, and that's glycogenolysis. That process is glycogenolysis, glycogenolysis. We're lysing our glycogen. But that's not where PKA stops. PKA phosphorylates other things too, including glycogen synthase. But when PKA phosphorylates glycogen synthase, that turns it off. And glycogen synthase would be synthesizing glycogen, but since it gets shut off, no more glycogen is being synthesized. So, through PKA's kinase activity, attaching phosphates to things, it turns on glycogen phosphorylase. And so now we're chopping up glycogen, we're mobilizing sugar, and PKA turns off glycogen synthase, which would have been synthesizing complex carbohydrate. It would have been anabolic with carbohydrate. Um, but it turns on catabolism and it turns off anabolism. And then here's a diagram looking at what we just talked about. In the liver, it's glucagon that's doing the glycogenolysis signaling, the PKA signaling. In skeletal muscle, there are no glucagon receptors. So, I mean, smooth muscle, there's going to be some, but not in skeletal muscle. In skeletal muscle, we have epinephrine that's initiating the signaling cascade. Same signal, though. Just different hormone that gets it started. And then we have the same basic signaling cascade once it gets going. And you know how it ends. Glycogen synthase gets turned off and glycogen phosphorylase gets turned on. And that was in muscle cell or that was in liver, that signaling cascade, two places where you store a ton of glycogen. But if we're in a fat cell, pKa phosphorylates different things. You can still turn on with with epinephrine, or nerves are innervated. So norepinephrine will turn them on too. Um, but pKa phosphorylates different things if we're in a fat cell. pKa attaches phosphates to perilipin and hormone-sensitive lipase in a fat cell, and that alters their behavior, the behavior of perilipin and hormone-sensitive lipase, and that initiates lipolysis, lipid lysis. We're lysing lipids, so let's get catabolic with fat. And that's it for this lecture. That last mode of enzyme regulation, of enzyme modulation, will lead us into the next subject, which is cell signaling for muscle hypertrophy. And that's mostly phosphorylation cascades. Attach a phosphate to a thing, which attaches a phosphate to another thing, and so on. So pKa signaling, which we went over today, that's catabolic enzymatic regulation. That's a phosphorylation cascade catabolically. But for anabolic, for regulation of skeletal muscle mass in hypertrophy, that's PKB signaling mostly. So that's what we'll talk about in the upcoming lectures, a lot of upcoming lectures about that one. But for this one, here are the review questions about everything we just covered, and I will see you in the next lecture.